Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. We have been discussing acids in our previous lecture, and in this particular lecture we are going to continue discussing the acid base controlled reactions. So, in the previous lecture we were discussing this as the last topic, and that is how natural processes and how natural reactions drive the pH of the system. Okay. So, I will just brush up this particular processes, the few processes, and I will go on continuing this. Okay. So, the very first equation that I would like to focus on is the carbonate dissolution. Again, it is an extremely important equation. Please try to write this equation on your own, the dissolution of carbon dioxide in water forming carbonic acid. So, when I am dissolving carbon dioxide and forming carbonic acid, my pH of the system is going down. Again, down means it is moving, the pH value is decreasing. Okay. The pH value is decreasing. That means it is moving towards more acidic conditions. Okay. If the reaction is such that the pH gets increased, okay, if the pH is increased, that is the value is going up, then I say it is a alkaline, it is causing more alkalinity, it is moving towards more alkaline conditions. Okay. So, CO2 dissolving in water forming aqueous carbon dioxide, which is again going to form carbonic acid. That H2CO3 is not going to remain stable, that H2CO3 will dissociate to H plus ion and HCO3, and that excess H plus ions is going to raise the acidity of the solution. Okay. So, this is an extremely important equation. Next, another one to note, very important, is photosynthesis. Okay. Photosynthesis. So, these arrows, okay, these particular arrows shows the direction of the reaction, whether the reaction is moving towards the forward direction or whether the reaction is moving towards the backward direction. Okay. So, for photosynthesis, so the reaction is moving in this direction. Okay. Carbon dioxide is utilized with water to form glucose. Now, there is no acid production. So, the gradual uptake of carbon dioxide from the system will make that system more and more alkaline. You are removing carbon dioxide from the system, right. On the opposite direction, if the reaction is moving, that is, rather than producing glucose, it is decaying. Organic matter is getting decayed or respiration is happening. So, either decaying is happening or respiration is happening. From both the reactions, carbon dioxide is getting generated. When carbon dioxide is getting generated and that is interacting and dissolving back in the water, then that reaction is making my pH go down. What do I mean by pH go down? Again, down means the pH is decreasing and it is moving towards more acidic conditions. Okay. Now, let us see another very important reaction, and that is chemical weathering of rocks. Okay. Now, chemical weathering. Now, rocks are made up of many types of minerals, okay, and alumina silicate minerals are the most common type of minerals in the rocks, and those rocks which are found on the earth's surface conditions. Okay. So, the earth's uppermost crust. Okay. Here there is more occurrence of the granitic rocks and igneous types of rocks. Okay. So, igneous rocks, out of which granite and there are variety types of rocks there, but the percentage of granitic rocks, okay, and also in rocks that are sandstones and all that, they also have certain types of rocks. Variety of sedimentary rocks will also have these aluminate silicate minerals. Okay. So, when this aluminosilicate rocks is getting weathered, okay, weathered means from larger minerals they are getting decayed into smaller particles. Okay, so they are breaking down, it is a breaking down of the rocks to finer materials. Okay. So, when that kind of weathering is happening, and of course, there are different agents of weathering. Okay. Weathering can happen due to physical agents, something like due to water activity, due to wind activity, due to glacial activity, due to waves and currents access. So, the a lot of physical power, whatever is there, that is causing the breakdown of the rocks. So, that is through the physical agents. Also there are chemical agents. So, chemical agents will work on the chemical properties of the rock and it will break down the system. Okay. And there pH is a very important variable there. If you are changing the pH of the system, then the rock is more susceptible to weathering. And what are the natural acids that is there? So, CO2, which is so commonly, it is basically there in the atmosphere. So, whenever it is getting deposited via rainfall, carbonic acid is interacting with the minerals. Okay. So, for example, this is K feldspar. Okay, it is type of mineral found in igneous rocks. So, that mineral, if it is interacting with the carbon dioxide that is dissolved in water, that is basically carbonic acid, then it starts decaying and forming kaolinite. Okay, it starts forming this particular mineral, which is basically a type of clay. Okay, it is a clay mineral, okay, kaolinite. Now, this particular reaction uses up carbon dioxide. So, weathering of silicate rocks is a significant sink of carbon dioxide. So, whatever carbon dioxide is there on the earth's atmosphere, that greatly gets trapped through these weathering reactions, and in the process bicarbonate ions are getting formed. Now, when bicarbonate ions are getting formed, what does that mean? The system is moving towards more alkaline conditions. Increasing bicarbonate ion means alkalinity increase. Okay. So, this forward reaction, will make the pH go up. That means, the pH value is increasing, that is, it is moving towards more alkaline, okay, alkaline conditions. Okay, it is moving towards more alkaline conditions. Now, let us see why do we need to understand acid. Why is it called, why is it pH is such an important variable that we measure always when we are discussing the water quality parameters, and anywhere you will go you will see, okay, there is a water quality study. One of the few parameters they always measure will be pH of the system, okay, because that drives so many equations and that also gives you the idea of what kind of system it is. Okay. So, first thing, what kind of interactions is happening due to pH? Let us see. So, aqueous interactions such as hydrolysis and polymerization. Hydrolysis means you are changing the ion, you are hydrolyzing the ion, okay, and then you are either creating more polymerization. So, ions that are there, they are dissolving, okay, you are either oxidizing or reducing, and then you can polymerize it. So, those kind of interactions is called hydrolysis and polymerization. Second thing, adsorption kind of reactions, okay, because protons, that means H plus ions. So, basically H plus ions, okay, they compete with the cations, and the OH minus ions, the hydroxyl ions, compete with the anions for the adsorption sites. Okay. So, whenever there is an adsorption based equation happening, if the pH of the system is varying, then it will start competing with the cations, while the hydroxyl ions starts competing with the anions, then they can start interfering with the reactions. They will not let the reaction to happen, because where it was, so we discussed about the surface controlled reactions, right, in the kinetics lecture. So, the surface is not available for adsorption for the cation interactions and the anion interactions, because they are occupied by these protons and hydroxyl ions. Therefore, it will not drive that particular reaction, and also it can affect the surface charge of the minerals. Okay. It can start getting adsorbed, and that will create a charge on the surface. Okay. If more positive ions are getting adsorbed, H plus ions are getting adsorbed, the surface becomes like that, right, it becomes charged. Then formation of metal ligand complexes. Now, metals, when they are dissolving in water, only the first alkali elements and alkaline earth elements and few other elements, okay, they are there in their free form, free ionic form. Most of the other metals, specifically the heavy metals and most of the transition metals, they will form some kind of complexes. And what are ligands? They are a particular kind of atom or molecule that will bind with this metal and increase its solubility. Okay. So, the solubility increases, or it can sometimes precipitate out also. Okay. So, that is a complex that is formed with the metal ion. Okay. So, for instance, OH minus is the most common inorganic ligand, okay, and it can be organic ligands as well. Okay. Organic ligands can have a very variety of chemical signature. Okay. The chemical formula of organic ligands can be very different. Okay. It can be highly variable. All kinds of carbohydrates, acids, molecules, protein molecules, they are all there in the water. Okay. And they are going to attract, they are going to form some complex with these metals. So, their interaction, okay, but since inorganic, among the inorganic ligands, OH minus ligand is the most commonly found ligand in the highest concentration, in one of the highest concentrations. Therefore, those complexes, so those metals whose PbOH is more soluble, okay, their occurrence or solubility increases, right. So, for example, in this figure you see as the pH decreases and the fraction, so the pH is plotted along the x axis and the y axis has the fraction of PbOH plus. Okay. So, the fraction of lead complexed as lead hydroxide is a function of the pH. If the pH is low, of course, the OH plus concentration will also be low, and so the fraction of PbOH will also be low. As you increase the alkalinity, OH plus ions, the occurrence increases, and PbOH plus ions, there also occurrence will increase. So, OH minus ions increases here in this direction, and therefore, the fraction of lead OH plus ion also increases in that direction. So, formation of metal ligand complexes, okay, depends on the pH of the system. Oxidation reduction reactions, another kind of reactions, okay, whether it is oxidation, if it is happening abiologically or biologically, it can produce protons, while the reduction processes, okay, the decaying processes, they will consume them, okay, and that has a huge effect on the solubility. So, here in this figure we have the pH in the x axis and the valence state, that is oxidation states, in the y axis of the different metals. So, here you can see if you are changing the pH, okay, if you are changing the pH in towards more acidic directions, then it will form this it will form this CO2OH minus, and if we are taking this into further, it will remain free as metallic ions. In these kind of figures, wherever there is a line, okay, that means the concentration is same, okay. But on this direction, whatever is the species written, their occurrence is more. For example, let us take this example of FeOH plus. So, at an alkalinity at the pH value of around 11, where is FeOH? Okay, FeOH will occur in the form of a FeOH plus ion. Okay, it will form it is there here. Okay, so if I take at 11, okay, so here is my FeOH plus. Now, if I try to shift it, if I am just decreasing the pH, okay, I am trying to decrease the pH, then it will start moving into the stability zone of aqua metal ions, okay, aqua metal ions. That means Fe2 plus, the occurrence of Fe2 plus will start getting stabilized here. So, this entire area, in this entire area, the aqua metal ion stability is there. In this particular area, okay, the hydroxymetal ions are more stable, while in this particular area, okay, in this particular area, the oxometal ions are more stable. So, these are called the stability diagrams. These are called stability diagrams. You can search and you can see the different stability diagrams, and we are going to further discuss this in the lecture where we are going to discuss about the redox reactions. Okay, so, I want to drive this idea that with the changing pH, okay, the stability of different species of ions get stabilized. Okay. So, the pH of the system controls, okay, the ion speciation, and some species of ion are more soluble, they are more bioavailable. Okay. So, if you are trying to understand, okay, what is the bioavailability of a particular element, in what species is it available. So, you always have to look at this kind of diagrams, okay, and see how the species is varying with the pH of the system. Okay. At that particular pH, what is the species that is going to be formed in the aquatic system, in what state it will be. So, when I am saying that chromium is present in 1 ppb is present, 1 ppb of chromium is there, it is not necessarily that 1 ppb is there in the form of Cr2 plus. Okay, it is not necessarily that. It can mean that this chromium can be in various forms. Okay. We need to understand what speciation it is, okay, and that is again a speciation is different, and I will talk about this kind of speciation in one particular lecture, how we determine that. Okay. Now, the solubility and rate of dissolution, I think all of you understand that we are adding pH to a system, the solubility increases. In fact, I think that if we are trying to dissolve metals, if you are working with metals, we generally try to dissolve things in acid. Okay. Acid is a dissolution. Generally metals do not dissolve in water, it will take a very long time. But what will dissolve, what will make it dissolve very faster? pH. So, you try to use acids for digesting sediments, for dissolving particular minerals. Okay. So, the solubility and the rate of dissolution of minerals is very strongly pH dependent. So, therefore, pH of the system can drive and change the chemistry of that aquatic system. So, it is extremely important to know what is the pH of the system, which components will be very sensitive to pH, what will precipitate out, what will get dissolve faster. So, all these kind of interactions you can understand by seeing the pH of the system. Now, let us go back to the overview. Now, we are going to see more practical applications of pH. Okay. But before that, let us see what ranges the waters fall. So, in natural waters, okay, the strong acids that we see is the sulfuric acid, HCl, bisulfate ion, ferric ion, FeOH2 plus and FeOH2 plus ions. Okay. Now, this is a chart of the pH showing the natural water composition and also comparing it with some values, okay, some other examples. Okay. So, for example, this is the normal range of stream pH, that is it can vary between 6 to 8. Okay. So, for rivers and small streams, depending on what kind of inputs it is having, what kind of weathering products it is receiving, in what kind of bedrock it is flowing through, the human interactions that it is having, all of this will control the pH of the system. So, this is mostly falling between 6 to 8. Okay. Then this is the precipitation pH, that is it is slightly acidic. So, a little below 5 and a little below 6. So, roughly you can say between 5 to 6.5, okay, is the pH of rain. Okay. Then this is sea water. Okay. Sea water has now a pH of 8.1. Okay. It is pH of 8.1. Then what is the pH of baking soda? It is somewhere between 8.5 to 9. Then milk of magnesia. So, basically magnesium hydroxide and all, ammonia, lye. So, these are more alkaline, increasing the alkalinity. Okay. In this side you have battery acid, that is lemon juice, vinegar. Now, let us see some important another important thing, that is acid rain. Okay. Acid rain can be anything that is less than 5 and it can go any lower degree of rainfall, any lower degree of pH value. But in this particular, within this particular value, okay, fish reproduction starts getting affected. Okay. That means it is, they are changing it, they are changing their biological nature, their eggs, their formation of new generation, there can be changes in the morphology of the fishes. Okay. So, their reproduction, their morphology, that gets affected beyond this particular pH. Adult fishes starts dying beyond pH of 4. Okay. It is too much acidic. Okay. So, they start dying. Let us see here, corals and ocean shellfish, they are less able to produce skeletons and shells beyond this particular value. Okay. So, beyond this particular value, their formation of exoskeletons, okay, their formation of exoskeletons gets harmed. Okay. Again, we are going to discuss this, the types of acids that is available, so organic acids can be humic acid, fulvic acid, carbonic acid, bicarbonate moves the alkalinity. Okay. Acetic acid is a very common type of organic acid in landfill leaches and sewage and all. And formic acid is also found in groundwaters, that is associated with hydrocarbons. Okay. So, decaying products, it gets accumulated, it starts accumulating, this particular formic acid gets separated out and it starts affecting the water, and that can change the pH of that particular system. For natural organic matter decomposition, humic acids and fulvic acids are very common. Okay. And they are very important because they can form complexes with the metals and they can help them transport in the transfer and the mobilization of these metals along the soil layers. Okay. Therefore, if you are traveling in the vertical section, okay, so if it is reaching the groundwater or if it is reaching across and as a runoff entering the stream, depending of what kind of grasslands and decaying and what kind of environment you are, it will change will start affecting the pH related mobilization of metals. Okay. So, those acids are very important. Okay. So, organic matter decomposition. pH of sea water, okay, which is about now varying from 8.11 to 8.15 at places. It reflects the presence of bicarbonate and carbonate ion, and to few extent some other species like boric acid and all. So, the pH of sea water is basically controlled by the carbon dioxide dissolution and formation of bicarbonate and carbonate ions. Okay. Now, values, now let us see some higher values. Okay. Some higher values are found in groundwater, okay, and those groundwater that is interacting with high calcium magnesium rocks, because they are start dissolving, they will start weathering, and that will produce that will start producing more bicarbonate ion during that interaction, and that bicarbonate ion will make it more alkaline. Okay. And in evaporitic lakes, higher bicarbonate again. So, the bicarbonate ions, they drive the alkaline, makes the system more alkaline in nature, as compared to H plus ions, which is driving it towards more acidic in nature. So, here in an example, so waters of volcanic exhalation, why it is so acidic? Because all the gases are getting going out, right. So, carbon dioxide, SO2, different kinds of nitrous oxides, all of them are coming out, they are dissolving in that water vapor, if it is raining, it is condensing into water, it will dissolve with those gases. So, they will come as their acidic form, they will dissolve and form their acidic form. Mine waters, generally why are they acidic? Because of different compounds are used to extract those minerals, to extract that particular not only the ore you are extracting, sometimes they can process it. So, whenever there is mining activity, there is higher interaction going on, those metals are going to dissolve, okay. It is more readily available for interactions, and that will drive the acidity of the system. Swarms, in swarms what is there? It can start getting very reducing conditions. So, the oxygen exchange with the atmosphere can get reduced. So, there is more decaying of organic matter there, that is there in that system for a very long time, because swarms are not places where there is a lot of free rushing water is flowing through. Generally, if there is a lot of free flowing water, it will continuously to get oxygenated. But in a swarm where there is the system is almost static and a lot of water is not continuously getting exchanged, oxygen exchange with the atmosphere is also very hampered and in fact insufficient as compared to the decaying that is happening, then those kind of environments will start becoming more reducing, decaying, and decaying reactions makes the system more acidic in nature. So, therefore, it is slightly acidic. Groundwaters, they are depending on their bedrock interactions, it can nitrate pollutions from nitrate fertilizers and all, that can change the pH of the groundwater. Rivers are mostly circumneutral, that means it is continuously receiving weathering products, therefore, that is driving the bicarbonate concentration in the river, okay. And in rivers there is a good buffering always available. So, therefore, the pH change in rivers is very difficult, and humans need to alter or intervene in a significant way, in a huge way, then only the pH of large rivers or streams can get altered. For small streams it is a different issue. For small streams or seasonal streams, it is very easy to change the pH, because the water flow is so less, weathering continuous flow of weathering products into the system is less. Therefore, the pH is very susceptible and can easily become acidic. Okay. But for large rivers and streams, it generally maintains that pH, it is buffered. Okay. Fresh lakes, again if it is a natural lake, fresh lake, then its value will be mostly towards related to the weathering side. If it is another kind of lake where there is a lot of rainfall, it is receiving a lot of rainfall, then it can start moving towards the lower end of the neutral conditions. Okay. So, a little slightly little less alkaline and more towards a neutral pH. Oceans average is 8.1, okay. Average we say it is now 8.1, but at different locations it can be little variable. Okay. So, it can vary from 7.8 to 8.3, and salt lakes where a lot of evaporation is happening. Okay. In those lakes it is seen it is very alkaline. Okay. Those are alkaline soda lakes, and you will see it is very precipitating out a lot of carbonate minerals and different types of other minerals. So, those type of lakes we are seeing extremely high alkaline conditions. Now, with this overview I will stop today, and in our next lecture we are going to discuss a few examples, okay, particular conditions where pH has been observed to modify the system, and we will see how it has modified those particular aquatic systems, and they are so relevant to the current global conditions. Okay. So, see you in the next lecture.